So today we begin therefore with position and momentum, and these are operators in quantum mechanics, and they have letters to denote them. X, we put a hat with it, that's a position operator. P, we put a hat on it, and the position and momentum operators don't commute, and the commutator is given by I h bar. Now, we have been dealing so far with wave functions. Our wave functions were these functions of x and t. They represent the dynamics of your system, the dynamics of your particle as it moves in time. But time, as you're seeing in quantum mechanics, is a little bit of a spectator. It's an arena where things happen, but the operators and most of the interesting things are going on without reference to time. Time evolution. You have an expansion of a wave function in terms of energy eigenstates at a given time, and then you can evolve it easily with the way we've learned, adding e to the minus I e t over h bar for each energy eigenstate. So time will play no role here. So when I talk about the wave function, at this moment you could put the time, but we will talk about the wave functions that have no time dependence. So say a psi of x wave function. So this psi of x may be the true wave function at time equals 0, or you could just simply think of it as a psi of x. Now, this wave function means that we're treating x in a particular way, and we say that we're working in the x representation, the position representation. Now, this means that we have an easy way to figure out what this operator does when it acts on this function. So when it acts on this function, it will give you another function, and the definition of this is that the position operator acting on the function psi of x is defined to be another function, which is the function x times psi of x. Well, we're talking about these wave functions and operators on wave functions, and a recurrent theme in quantum mechanics is that we will think of wave functions, sometimes we call them states, sometimes we call them vectors, and we basically think of wave functions as vectors. And things that act on wave functions are the things that act on vectors. And the things that act on vectors, as you know in mathematics, is matrices. So we're compelled, even at this early stage, to get a picture of how that language would go if we're talking about these things. So how do we think of a wave function as a vector, and how do we think of x as a matrix? So there is a way to do that. It will not be totally precise, but it's clear enough. So suppose you have a wave function, and we're interested in its values from 0 up to a. This wave function is a function of x between 0 and a. So it's a psi of x for x between a and 0. That's all the information. What we're going to do is we're going to divide this thing, this line, this segment, into a lot of pieces, and we're going to say, look, instead of writing a function like sine of x or cosine of x, let's just give the values and organize them as if this would be a vector of many components. So let's divide this interval in sizes epsilon such that n times epsilon is equal to a. So there are n of these intervals. So we think of psi as a vector whose first component is psi at 0. The second is psi at epsilon. The third is psi at 2 epsilon. And the last one is psi at n epsilon. And depending on how much accuracy you want to work with, you take epsilon smaller and n larger, keeping a constant. And this would be like summarizing all the information of a function in a vector. Now, that's intuitively a nice way of to think of it. May look with your background in classical physics a little strange that we sort of put the value at 0 along the x-axis, first component, the value at epsilon along the y, the value of 2 epsilon along the z, but we need more axes, so you need many axes here. In this case, this is a n plus 1 column vector. It has n plus 1 entries, because 0 up to n, that's n plus 1 entries. But that's a fine way of thinking of it. Not exact, because we have an epsilon. In this way of thinking about the wave function, we can then ask, so how does the matrix, what does the matrix x hat look like? So x hat is an operator, and it acts this way. So here is how it looks like. We would think of x hat as an n plus 1 times n plus 1 matrix. And its entries are 0 everywhere except in the diagonal, where they are 0, epsilon, 2 epsilon, up to n epsilon. And here's a big 0 and a big 0. This, I claim, is the way you should think of the x operator if you thought of the wave function the way we wrote it. And how do we check that? Well, x operator acting on psi should be this acting on that. And then, indeed, we see that if x hat is acting on psi of x, what do we get? Well, it's easy to multiply a diagonal matrix times a vector. Here you get 0 times psi of 0. You get a vector, so let me make this thinner. Then I get epsilon times psi of epsilon, 2 epsilon times psi of 2 epsilon, up to n epsilon times psi of n epsilon. And indeed, that matrix looks like the matrix associated with this wave function, because here is the value at 0 of this wave function, here is the value at epsilon of this wave function, and so on. So this has worked out all right. We can think of the wave function as a column vector and then the position operator as this vector as well.